Hello everyone and welcome to the coronavirus edition of our fifth exercise from our signal theory class. Today we will start practicing spectral leakage and how we can suppress it. Go to Moodle and there in the folder exercise 5 find this signal x.mat. This signal actually has 3 pure tones, 3 sine functions in it, and we will use spectral analysis to find the frequency of those 3 sine waves. When you download the signal into your computer, into MATLAB, you will load it like this. And I know that the sampling frequency of this signal is 1 kHz. Now that I have everything loaded, I can take a look at my signal. And this is it. This is my signal. Okay, I can see that this kind of looks like a sine wave maybe, but I do not see that I would have 3 tones in this signal, 3 sine waves. For this I need to take this into the spectral domain and take a look at the spectrum. So let's take a look at the spectrum. I will label axis. And this is my spectrum. So I can see 2 spikes, but I will remember that this is the DFT spectrum, so this right side is just a mirror image of this left side. So it would seem that thus far I can see 1 peak here, and that would correspond to 1 pure tone. When I zoom in, I could be able to read the frequency, but I must remember that this is still DFT spectrum, so on the horizontal axis I still have indices of DFT, and to be able to read the frequency in hertz I need to properly scale this horizontal axis. So let's first do that. How do I scale that axis? Well, I need to take the length of my spectrum. Then I need to generate the vector of indices. And then I need to properly scale it so that I will get this vector of frequencies in hertz. Now I can use that vector f for my horizontal axis, and when I do on the horizontal axis I will have hertz, and my spectrum will be function of that frequency f. And now I have it. Now I have the horizontal axis in hertz, so when I zoom this in, I can find that my frequency, my first frequency that I have discovered is at 152 hertz. So I have found frequency of one of my tones, but I have told you that I have 3 tones in this signal. So where are the other 2? Well, this is the exercise on spectral leakage, so they are probably hidden in the spectral leakage. But where is that spectral leakage? I mean, you do not see nothing like I showed you during the lecture. On the lecture I showed you those side lobes that were spectral leakage. Why do not we see them here? Well, the problem is the DFT spectrum. Even though the MATLAB is plotting it like the continuous line, the DFT spectrum is actually discrete. So to plot it correctly, I should actually use stem here. Now I have emphasized the discreteness of the DFT spectrum. And now I need to realize that these discrete samples of the DFT spectrum are just samples of a continuous DTFT spectrum that we were working with during the lecture. Let me show you that on the picture. So here I have a picture, and during the lecture we were working with this blue DTFT spectrum. That is a continuous function. When we use DFT, and in MATLAB in real life we have to use DFT, then this blue spectrum cannot be represented in a computer, it has to be sampled. So in MATLAB we will get these black samples of this continuous spectrum. And the problem is that MATLAB is sampling this continuous spectrum very coarsely. You can see that you are getting only 1 sample per this lobe. And that is why you do not see those lobes so nicely as I showed you during the lecture. But you can actually improve this. The MATLAB by default is giving you as many samples of the discrete spectrum as is the length of your signal. Our signal has the length 250 samples. So by default, MATLAB is going to give me 250 samples of my spectrum. If I want to increase this, get more samples, get finer sampling, I can actually use a second parameter of this FFT function. And here I can require to have, for example, 5,000 samples of the spectrum. So now that spectrum will be sampled in 5,000 points, that it will be sampled much more finely. Okay, let's run that. Now this is a mess because I'm still using stem, so I will go back to plot. And here I have it. Now I can see that spectral leakage much more clearly. Okay, at this point I will make things slightly easier to look at. I will just plot only this left hand side of the spectrum, so I will go only from 0 to half of the sampling frequency. Okay, here I go. Now I will not be bothered by that mirror image. Okay, let's go back to that spectrum. So now I have this peak. I can clearly see that in the spectrum is one sign, one tone, and I can read its frequency. And now I can clearly see the spectral leakage. But where are those other signs? Well, they are probably hidden in that spectral leakage. So I will need to get rid of that spectral leakage. How do I do that? Well, before computing the Fourier transform, I'll need to multiply my signal with a window. MATLAB can generate some nice windows for you. At first we will use so-called Hamming window, and for that we will use function Hamming. This function has only one parameter, and that is the length of the window. We are going to multiply our signal with this window, so we need that window to have the same length as is the length of our signal. Like this. Okay, now I can multiply my signal with that window, and only now I will take that Fourier transform. I will assign this to some x2, that will be my second spectrum. Here I want to be careful. Let's take a look at the size of my signal. I can see that it has 250 samples and it is a row vector. Now let's take a look at the size of my window. It too has 250 samples, but it is a column vector. So for these two guys to fit together, I need to transpose one of them. I need to do this. And I will too use that computation of FFT in higher number of samples. Now that I have done that, I compute my spectrum like this. I can plot it. And just to be able to see both of those spectrum in the same plot and be able to distinguish between them, I will make the first one green and I will make the second one black. And here I go. The green spectrum is without suppressed leakage. You can see a lot of leakage here. The black one is with suppressed leakage. You can see that there is much less leakage here. And at this point there seems to be like a very small peak that might just be my second sign, my second tone. I can see it very badly, and the reason why I see it very badly is that I'm using a linear scale on my vertical axis. And as I told you in the last exercise, it is not a good idea with spectra to use a linear scale on your vertical axis. So now I will use decibels on my vertical axis to see this better. I will compute the logarithm of the spectrum, so I will have the logarithmic scale. And here you have it. So now I have decibels on the vertical axis, and now I can see those weak parts of the spectrum very clearly. And although I can see very clearly this second peak which corresponds to that second sign, to that second tone, and had I not removed that spectral leakage, this second tone would be hidden in that spectral leakage. So now we can see two tones in my spectrum. Now I can read the frequency of the second one, which is something like 184.7. But where is that third tone? Well, to find the third tone, I need to use a window which has even better suppression of spectral leakage. And for this we will use so-called Blackman window. In MATLAB I can generate this with the command Blackman. And I will compute my third spectrum. And plot it. And let's make this one red. Here we go. So in red, I can see the spectrum computed with the Blackman window. And you can see that the Blackman window has the best suppression of the spectral leakage between these windows that we have tried. And here I can see my third tone. So I not only need to somehow suppress that spectral leakage, I even need to pick a good window to do it, to be able to see this third sign, this third tone, and now I can read its frequency, and it looks like it's something like 250 Hz. So this is how you need to compute your spectrum. You do not just take your signal and compute FFT, that is the computation of the discrete Fourier transform. It is always a good idea to weight your signal with a window. At minimum, it's recommended to use at least Hamming window. If you have suspicion that your spectral leakage is still too strong, you can try Blackman window. And if you do not do that, some parts of your spectrum may get hidden in the spectral leakage. Okay, now what about that spectral resolution I was talking about during the lecture? I told you that the longer the signal, the better the spectral resolution. Or the shorter the signal, the worse the spectral resolution. Let's take a look at that. What happens if I use this spectral analysis, but I will use shorter signal? So the original length of my signal is 250 samples. What happens if I use only 150 samples? This is me limiting the length of the signal to the first 150 samples. Let's take a look at the spectrum, how it changes. When I do that, you can see that these peaks associated with those individual tones get wider. If I shorten the signal even more to first 100 samples, now these peaks get even wider, and you can see that they are starting to blend together. If I use even shorter signal, now it's everything blended together, the spectrum is a mess, and I'm not able to recognize those individual frequencies, those individual tones. In this case, I have insufficient spectral resolution, and to improve this, I need to use longer signal. So I need to go back, and when I used the entire length of the signal of 250 samples, this is how the spectrum resolution improves. Also, what is noteworthy, when I zoom this in, you can see that the best spectral resolution, the narrowest peak that is provided, is given when I do not suppress spectral leakage. When I suppress spectral leakage, then my peak associated with a single tone gets wider and wider, which decreases the spectral resolution. And when I use Blackman window, you can see that this peak is the widest, so the spectral resolution is diminished the most. So there is a little bit of trade-off between the spectral suppression and the spectral resolution, but the biggest influence on the spectral resolution has the length of the signal that you are working with. Okay, now let's take a look at the design of FIR filters using the window method. Let's design a low-pass filter. During the lecture, I showed you that you can start in the continuous time spectral domain, compute the inverse Fourier transform, and get the continuous time impulse response. And then you can sample it. You can actually simplify this a little bit. I showed you this longer route for educational purposes, but you can actually skip this first step. You can actually start in this discrete time frequency domain and compute the inverse Fourier transform from here to get my discrete impulse response. The only thing you need to be aware of here that here you will be working with normalized frequencies. So to specify this corner frequency, I need to recompute it from frequency in Hertz. Typically when I design my filter, I think about my frequencies in Hertz. So how do I do that? Well, we have done this before. This corner frequency in Hertz to the sampling frequency must be the same as this normalized corner frequency to 2 pi. I have it here. Corner frequency in Hertz divided by the sampling frequency must be the same as normalized corner frequency divided by 2 pi. So from here you get this expression for the corner frequency. With this taken care of, we can go back to computing our impulse response. So I need to take this frequency characteristic and take the inverse Fourier transform, the inverse discrete time Fourier transform to get my impulse response. I have that here. This is the definition integral of the inverse discrete time Fourier transform with the frequency characteristic, this frequency characteristic substituted. And here I evaluate that integral. I need to integrate only from here to here, and I will be integrating 1. That is here. When I do the integration, I get this. When I substitute, I get this. And when I simplify, I get this. Just watch out, you are dividing by n here, so this is valid only for n different from 0. When n is equal 0, you actually need to substitute that 0 here and evaluate this integral. When you do, you get this. Okay, so this is my impulse response, and now I can take it to MATLAB and check it out, what kind of filter I have designed. Okay, so first, type in the impulse response. Now, what do I need to define here? Let's start with omega sub c. And that should be, I'm taking it from here, and I need to define my sampling frequency. So let's say in this example, I will do this for sampling frequency of 10 kilohertz. And the corner frequency, that is this frequency, I will set to 2 kilohertz. Now I need to set this n. This n should ideally go from minus infinity to plus infinity. Well, such a filter would take a very long time to compute, so we do not have time for that. So we need to cut this to a finite length. And let's say at first I will set my filter order to be 20. So if my filter order is 20, I need to take 21 samples of this impulse response. Why? Well, recall what the schematic of an FIR filter looks like. If I have order 2, then I will need 3 coefficients. If I have order 20, then I will need 21 coefficients. So my n will go from minus m divided by 2 to m divided by 2. And this will give me 21 coefficients. Okay, so here I have generated my impulse response. Always a good idea to take a look what you have done. And here I go. Okay, here I have a hole in the middle. Why do I have a hole in the middle? Well, because I have omitted this part. Here I'm dividing by 0, and that is just giving me a number which MATLAB is not going to plot. So I need to add that for n is equal 0, my impulse response is omega sub c divided by pi. And here I have my impulse response. If I want to make the justice to it being discrete, I can use stem. And here I have my discrete impulse response plotted discretely. Okay, so I have designed some filter, I have designed an impulse response. So let's check it out and let's try to generate a signal and let's try to filter it. So I will generate a signal which is composed of two sines. The first sine will be at frequency f1 and the second sine will be at frequency f2. I will set that frequency f1 to be 200 Hz. It should have been 100. Okay. Okay, so I have designed some filter, I have designed some impulse response. So let's check it out, generate a signal, and let's try to filter it. So I will generate a signal which is composed of two sines. The first sine will be at frequency f1, and the second sine will be at frequency f2. I will set my f1 to be 100 Hz, and that is a frequency which should be passed by my filter. The corner frequency is 2 kHz. This frequency is 2 kHz. The second frequency f2 I will set to 3 kHz. That is something which should be suppressed by my filter. I still need to define the vector of time. It will go from 0 with the step of sampling period to some time, uppercase T. I will set the length of my signal to be 50 milliseconds and the sampling period is 1 over the sampling frequency. Here I have my signal generated, so now let's filter it. The filtering is convolution, so I need to convolve my signal with my impulse response. And that is it. So let's plot the result. And this is it. So this is the original, this is the input signal, and you can see that it is a composition of a low frequency sine wave and a high frequency sine wave. And this is the filtered signal. And you can see that the low frequency sine was passed and that high frequency was suppressed. But that high frequency was not suppressed ideally. You can still see it wriggling here. Why is it still passing? Well, to examine why my filter is still passing my high frequency signal, I need to take a look at its frequency characteristic. So to find out what my frequency characteristic is, I need to compute the Fourier transform of the impulse response. And I will do this in 2000 points so that I will get very nice fine sampling. Before I plot this, I will prepare my horizontal axis so that it is scaled in Hertz. It will be very easy to read that frequency characteristic for me when I have the horizontal axis scaled properly. So for this purpose, I need to find the length of my spectrum. I need to generate the vector of DFT coefficients and then recompute it so that I will have it in Hertz. And now I can plot it. And label the axis. And here you go. This is my frequency response. I will add some nice grid here. So when I have two frequencies and one frequency is 100 Hz, that will be here, and you can see that this signal will be passed with amplification which is close to 1. Then I have that second frequency which is 3 kHz, and that is going to be here, and you can see that that is going to be amplified with amplification of something 0.05. So it is going to be attenuated by 20 times approximately, but it's not enough to get rid of the frequency completely. You can still see that it is seeping through. So how can I get rid of this non-ideal stop band? Well, as I told you during the lecture, I cannot just cut my impulse response to some finite length. I need to weight it with some smooth window. So let's check out the Hamming window first. I will do it here. I will take my impulse response and I will multiply it with a window, and that window I will set to be Hamming window. The length of Hamming window needs to be the same as the length of my impulse response. Like this. Here again I want to be careful. I want to check that the size of my impulse response is this. It is a row vector, and I need to remember that MATLAB is going to generate the window as a column vector. So for these two guys to fit together, I need to transpose one of them. Like this. And now I can run this, and two things happened. First, let's take a look at this signal, and you can see that now I am passing only that low frequency signal, and that high frequency signal is being fully suppressed. And also you can take a look at the frequency characteristic. You can see that my pass band is nicely even, very close to 1, and my stop band is very close to 0. But during the lecture I pointed out that this is a little bit lame filter because I have very slow transition from the pass band to the stop band. This transition band is very wide. What can I do to improve it? Well, from the lecture you need to increase the length of your impulse response. You need to take more samples. That means that you need to increase the order of your filter. So let's try it out, and let's increase the order to 50. This is my original frequency characteristic, and now that I recompute it, you can see that it is steeper. This transition band is more narrow, and when I increase this even more, I get this, and even more, I get this. So you can see that when I want to get close to that brick wall filter, I need to use order of couple of hundreds. At this point, it is worth pointing out that this filter is going to have some delay. It takes some time for the signal to seep into those delay lines so that filter can actually do something with that signal and put something reasonable at the output. When you have a filter which has the impulse response symmetric like this, then the delay is going to be half of the order. So if I have the order 200, in this case the delay is going to be 100, and that is what you are seeing here. It takes about 100 samples for the filter to start doing something. Another thing which you should note is that in this stop band, the frequency characteristic is not exactly 0. It looks as if it was 0, but it is just because I'm using linear scale on this vertical axis. That is usually a bad idea, so I should use logarithmic scale, and that will allow me to examine this stop band better. So let's do that, and let's put our frequency characteristic into decibels. And here I go. Now I can see that frequency characteristic in the stop band much better. Now I can see that that Hamming window is giving me suppression of about minus 50 decibels or more. I can actually increase this. I could use Blackman window. And the Blackman window is going to give me something like minus 70 and more. But you may get tired of switching these windows back and forth, trying different types of windows. Instead, you could just use one window, which is called Kaiser window. And this Kaiser window has a second parameter, beta. And by setting this parameter, you can actually change the suppression in your stop band. So if you set it to 1, you will get suppression of something like minus 22 decibels and more. If I set it to 5, I will get suppression of more than 50 decibels. If I set it to 10, I will get suppression of more than 100 decibels. So this is how you can design filters with Kaiser window, and you will set suppression in the stop band just by changing this parameter beta. This is what we typically use when we pick windows for our filter design. Now let's take a look at IIR filters. You need to be able to draw a schematic, you need to be able to determine the order, and you need to be able to write a difference equation. Also, you need to be able to read these coefficients. So you can see a schematic like this, and from there you need to be able to read coefficients, write them like this, and write the difference equation. Or if I give you the difference equation, you still need to be able to recognize the coefficients and draw the schematic. Or I can give you the coefficients and you will need to be able to draw the schematic and write the difference equation. So let's take a look at that. First, when I have this schematic, how do I read those coefficients? First, feed-forward coefficients. Those are very easy. This is B0, this is B1, this is B2, this is B3. Now those feedback coefficients. This is actually 1 over A0. So A0 is 2. This is actually minus A1. So A1 is minus 0.2. This is minus A2. So A2 is plus 0.2. And this is minus A3. So A3 is minus 0.3. This is where I have written that down. If you want to put this into MATLAB, typically you do it like this, and then you can use these vectors for that function filter. And when you just use this general formula and substitute those coefficients, you will get your difference equation. This is a general form of difference equation. If you actually want to implement it somewhere, you need to solve for this output signal. When you do that, you can rewrite the difference equation into this form, and that can actually be implemented. Let's play with IIR filters in MATLAB. So far you do not know how to design an IIR filter, so I have designed an IIR filter for you. You can go to Moodle, to that directory exercise 5, and there you will find this file coefs.mat. Download it into your computer and then you can load it to MATLAB like this. When you run this, it will load to MATLAB two vectors B and A, and in the vector B you will have your feed-forward coefficients, and in the vector A you will have those feedback coefficients. You can see that I have 3 feed-forward and 3 feedback coefficients. That means that I'm dealing with a filter of order 2. Now I know that I have designed this filter for sampling frequency of 800 Hz, so I will write that down. Now let's find out what this filter does. So far you do not know how to compute the frequency characteristic of an IIR filter efficiently, but you know a way how to find the frequency characteristic of any filter. You just need to get its impulse response. And how do we get an impulse response of an IIR filter? Well, if I can implement that IIR filter in MATLAB, then I will just feed it a Dirac delta pulse and the result will be the impulse response. So let's just first generate that Dirac delta pulse. First I will generate a vector of zeros. And then on the first position I will put 1. That will be my Dirac delta pulse for 0 and positive values of n. Now I can filter it. And the result will be my impulse response. At least the first 400 samples of that impulse response. So let's plot it. And this is the impulse response of my filter. I will label the axis. And here I go. Okay, now that I have the impulse response, it's quite easy to compute the frequency characteristic. I just need to compute the Fourier transform of this impulse response. So let's do that. this is it. Before I plot this, I will create a vector of frequencies which I will use for my horizontal axis so that my horizontal axis is properly scaled in hertz. For this I need to get the length of my spectrum, generate the vector of DFT indices, and scale them like this. And now I can plot my frequency characteristic. Label the axis. And here it goes. This is my frequency characteristic. And what does this filter do? Well, it seems to be passing at almost all frequencies, except this very narrow band around 50 Hertz. So this appears to be a band stop that is suppressing at frequency of 50 Hz. This could, for example, suppress power noise interference. If I had ECG with power noise interference, I could use this filter to suppress that power noise interference. And it just so happens that I do have an ECG corrupted by power noise interference in this directory exercise 5. So go ahead, download this signal, and we will test our filter on this signal. You can load that signal into MATLAB like this. This will actually load a variable ECG into MATLAB, and in that variable you will have that ECG with that power noise interference. And now we can filter that ECG like this. In this vector Y, I will get the filtered signal. So let's take a look at it. And this is what I get. This is my original signal. You can see that it is ECG corrupted by the power noise interference, and this is my filtered signal. You can see that the power noise interference is suppressed. Interesting thing to note is that I was able to do this filtering using a filter of second order. So this is a very computationally efficient filter. On the previous exercise we did this by filtering in the spectral domain. For that we had to use much more computational power. So this IIR filter is actually more computationally efficient. Another thing to note, and this is just some nomenclature, you can see that the frequency characteristic of this filter has this notch in it. That is what creates the band stop. And that is the reason why this type of filter is called a notch filter. Let's take a look at one more trick which you can do with the frequency characteristic. I will take as an example this filter which I analyzed during the lecture, and I showed you that it has this frequency characteristic. When I substitute for this coefficient A1, I will get this specific frequency characteristic. Also, this filter has this difference equation. Now the question is, if the input of the filter is this sign, what will be the output of the filter? Well, you would find that it is kind of difficult to compute the output analytically from this equation. But you know the frequency characteristic, and the frequency characteristic tells you how the individual frequencies are being passed through the filter, how they are being amplified and phase shifted. And this sign is just a single frequency. What frequency? Well, this sign sits at normalized frequency 0.1. So if I want to find out how it is being transferred through my filter, I need to take a look at the frequency characteristic at frequency 0.1. When I substitute, I get this expression, and when I evaluate this in MATLAB, I will get this. By the way, this is the code which you can use in MATLAB to get this. And when I take a look at this is the magnitude of my frequency characteristic, and that is going to tell me how the signal at this frequency is going to be amplified, and this is the phase of my frequency characteristic, and that tells me how the signal at this frequency is going to be phase shifted. So if this is my input signal, then this is going to be my output signal. It's this signal, except it is being amplified by 1.98, and it is being phase shifted by minus 0.099. And I can get this purely from the frequency characteristic, and I don't need to compute this difference equation. You can actually use this for different sines and cosines. Let me show you one more trick. What if the input of the filter is just this constant? Well, this constant is just a cosine at zero frequency. So if I want to find out how a constant is being passed, then I need to take a look at the frequency characteristic at zero frequency. When you substitute for this filter, you will get this. The frequency characteristic is just number 2, which has zero phase. So the output of the filter is this. It's this function multiplied by 2 and not phase shifted. So if I feed this filter a sequence of 1s, I will get a sequence of 2s. Last, what if I combine different sines and cosines? What if I combine at the input of the filter, for example, this one, which is cosine at zero frequency, and this sine, which sits at frequency of 0.1? Well, if you have a combination like this, then you just need to take it element by element. So this is at zero frequency, and it is being transferred like this. So at the output, this will create number 2. This sits at frequency 0.1, so it is being transferred like this, and at the output it will give me this. So this is how you can evaluate how arbitrary combination of sines, cosines, or a constant is being passed through your filter, just by using the frequency characteristic.